Well, this is my project for electrical projects. So first off, during testing, you want these power supply, load tester, and what that does is it gives you 5 volts to this specific chip, which is a differential voltage amplifier, and turns that voltage into a current, which you can then turn back into voltage with this resistor, giving you range to adjust what voltage that you want for this. Like if you have a big range from 0 to 5 amps, like I do, you want a very high resistor so that you can read the entire range. But if you're only going from 0 to 1 amps, you can have more precision with a smaller resistor. And first, we have the 5 volts coming in, which goes to the power of the chip, and then to the plus side, which you can see, which is, can't really see it. It is the one side of the 50 milliamp resistor. Pin 24. As the plus side, it takes the difference of that to pin 25, which should be, because in this configuration, you have power coming in through here, going across the resistor, and then out. This is where it's being drawn from. So we're drawing power from plus 25. We will get a voltage drop, and we can see that if we have 1 amp drawing, we have 4.3 volts on the output. That's probably due to our power supply. We have 1 amp drawn, but we can see here that it's actually 1.2 amps. That shows that this chip actually draws 200 milliamps to operate. But if we look at our display, we see a couple things. We see a Vout, IS, and iReal. Vout is the voltage it is reading. IS is the total current that it thinks is outputting. So that would be the current that the chip uses, and the current that you are drawing. Say, charge a battery, drawing on 1 amp, it's showing that you're drawing 1 amp. Next, we have the iReal, which is the current that it thinks it's drawing. We can see here that's very not accurate. That's due to any effector. I mean, it doesn't really matter too much. It's just due to the equation being wrong, but that can be changed later in the code. That's fine. Say that for later. It thinks that you are using this much power, this much current. That's it. Nothing much to say about that. Things using that. But one thing to note is that even if this is offset from 1.1 amp to 1.3 amp, it is still a linear slope. So if we have 5, it is 0.6 minus the 0.2. So it is still linear, just not entirely linear to the point where you can pick any random voltage and say, or any random current and say, this is exactly what it knows it's drawing. Next, we have the switching circuit. Sorry, I need to set it up. I only have 1 load tester and I can't do anything else with it. Okay. So we turn on the voltage. We will get 8 volts across that. Just for clarity's sake, I will turn up the potentiometer all the way to the top. You can see that the voltage adjusts. Okay, here we see a couple things. First, as you see, I have multiple channels. This is the input of the LM2679, the 5 amp one, input output. This is the input output voltage for the 1 amp one. It's 5 amp, 1 amp, yellow is input, blue is output. I will turn off these 2 channels so we can just see the main waveform. Okay, if we measure it, this is around 32 volts, and channel 2 is around 25, which lines up with our power supply or our load tester. Okay, now we are a couple things. The max current you can draw is different from what the current you can draw continuously. So we are currently drawing a load of 100 milliamps, and you see that the voltage is very spiky, but not so much that's about a voltage of spike, which is fine. In fact, our voltage on the input is spiking from about 1 volt. I can't change it to be any less than that. We're in here. What is it doing? we see this specifically. So that's about plus or minus half a volt, so 1 volt up and down. And then this is our outputs, which we can see is on the same channel, or same volts per division, sorry. And that is half a volt from the top to the bottom, which is great. That's pretty precise. Okay. This is with a load of 100 milliamps. And if we try to go up, watch this voltage here. It stays pretty consistent, drops a bit, and then once you get about 1 amp, it starts to drop really badly, and once you get to 1.1, 1.2, it dies. But that is fine. That's within acceptable. I wanted 5 amps, but the peak current that it draws is different than what it can continuously do, because if we look here, when we're outputting, the peak current is what it's rated for, which is this 5 amps, and that is this peak right here. It won't do that on a breadboard, at least. We were not going to do 5 amps. But I don't think I'm going to do 5 amps in general, unless I get a PCB, but that will be later. You get 5 amps right here, which allows it to charge for a bit until it starts to switch again. Next, we have showed you that it drops down 1.2, but that's different between what it can do all the time. So see right there, I'm going to continue to make this draw 1 amp, and when I turn the power supply, let's see, it likes to change its mind sometimes. So it doesn't like 1.2, but if you turn on 1.2, it also drops. Sometimes it can be different. That is due to parasitic things. So if we actually wanted, see, if I went up 1.4 volts, 1.4 amps, and then it's like discharge 7. So it's different what you do than what you can draw, or when it's continuously on is different than what you can draw when it turns on. That's fine though, because to be honest, a nice round number like 1 amp on or off is fine, and that's pretty good. Next, we have, if I turn off these 2 channels, turn these ones, output, I'm gonna change the load tester. We can see the voltage of 9 volts, boom. And if, oh, that's fine. Well, you can actually see one of the problems that I found. The input voltage likes to go up and down, but that's fine. I can probably change it later. And the Arduino, I think, is rated to not exceed 1 amp, draw 1 amp, but that's fine. 800 milliamps with constantly 8.2 volts, which is in the acceptable range of 7 to 12, means the Arduino will be powered no matter what. Also, it means that the 200 milliamps, then you have a bit of play here of current to send to the INA, which is better because I found that the 5 volts of the Arduino is very poor. So you send this voltage out to the INA to get your differential current. Then you can you can do whatever you want with that reading. And then you have this chip, which I actually can't really test, but there's a problem where it overheats itself after a bit. Honestly, I don't think it's necessary. As long as you use the included one, you don't need to worry about it. And I realized that you can just put a sticker on the box that says, hey, this is 36 volts. Don't do it. Okay. I think that's everything. Just to recap, oh, that was a little spark. Just to recap, you have an adjustable voltage of 1.2 or 1 volt, it's whatever it is in internally, down up to 24 volts, which means we have a 6 volt drop. We have a 6 volt drop because we are inputting 32 volts, or we have an 8 volt drop, or because we're inputting 32 volts. And you can see the ripple here, and you probably can see the ripple if I switch it to the other one. That's the ripple for the nano voltage. there's the ripple for that. All the acceptable range of 1 volt. If we're talking efficiency, we could do a quick calculation. How much power are we at? Actually, I don't think I can. I don't know if I'll be able to, but we are currently drawing 800 milliamps at 8 volts, and we're only sucking back 300 milliamps from the source. And if we turn up the voltage, our current should rise just a bit. Or, sorry, I'm on this other one. Also, as long as we're not drawing load, you can see our idle current consumption is about 5 milliamps. So if that's with this one, if that's with 32 volts, let's see, probably like not even 100 milliwatts, or maybe a little over 100 milliwatts. Yeah, 150 milliwatts, give or take. And we can see that if I draw 800 milliamps at this, I'll draw 800 milliamps and I will turn up the voltage. You can see that our current that we're actually drawing starts to go up because we're drawing more current. Efficiency. So if we look here, we're having 16 watts, 16.4 watts, and we are drawing 32 volts at 600 milliamps. So 32 times 0.69. We do about 74% efficient, if my calculations are right, which is not the best, but that's to be expected. One of the main drawbacks around this chip is because the efficiency varies with so many things, 3 factors: the voltage you're putting, the load you have, and how much voltage you want out. The efficiency of the chip kind of sucks, but as we saw, turns on at specific voltage, the output voltage is very clean, meaning that for charging your battery, for a stable electronic circuit, it'll be fine, it'll power it, and you'll be stable. This is, I think, the end of the main section. Kind of just going to talk about the TPS. I think I'm just going to not deal with it anymore. The TPS, I actually can't work with it unless I have a printed circuit board that's big with multiple ground planes, because I was playing with it earlier and it was working, but it starts to heat up and then it starts to pulse skip when it shouldn't be pulse skipping. It should change its duty cycle. And with how hot it is, I'm thinking it is thermally shutting down for a bit until its temperature drops. It goes, and then it starts until temperature drops. It turns back on and works. But that's everything. It works. Ideally, I could have charged a phone, but that would be a couple minutes of effort. I was thinking just put a USB-A port here and then have it plug into my phone. But I don't have a charger for that, so can't do that. Yep, that's my project. That's everything. I guess I could go more technical jargon, but not for this video.